A good student wanted me to review, and I didn't have time, so I'm making a video. Yeehaw, another video. Just kidding, but maybe it'll help. They wanted me to review, what am I talking about? Oh, yeah, the graphing techniques that we use in kinetics, kind of to summarize the different um, shapes of curves and mathematical equations that help describe them. In any case, let's start. It's kind of a mini quiz if you want to quiz yourself. What would this graph tell you? If I graphed the concentration of a reactant versus time, and it resulted in a linear decrease over time, you can pause the video or not, or I'll probably print these PDF pages so you can go back and quiz yourself again if you'd like. Oh, the answer is, well, it seems like the concentration of A versus time, the rate law, would be zero order in A. It's almost never, but there are quite a few reactions that do not depend on the concentration of A. And in other words, the rate is simply equal to some constant little k. And the concentration of A, the amount of A, just linearly decreases until it reaches nothing. You can look up the equations for half-life. They're given to you on the exam. But the key here is the half-life is not constant. The half-life, the time it takes for half of A to decay away into something else, depends on the initial concentration. That's an interesting thing. The half-life changes. What would this graph tell you? Jeopardy music. Scratching my head. I don't know. Oh, interesting. Looks like we graphed the reciprocal of the concentration of some reactant B, and that ended up being linear. Oh yeah, that means the reaction order is first order in B. In other words, here are the equations. Ooh, too fast. No, it's not first order. It's second order. Okay, my brain's on vacation. That's my only excuse. Yeah, so it's second order in B if the reciprocal linearizes the data. This is the reciprocal of the original concentration, B naught, and we just increase linearly from there. The equation describing the straight line is the reciprocal of B equals the reciprocal of B naught plus KT. T is the time. Oh, and so you might recognize that as a y equals y equals mx, x-axis plus b. Coincidence, that's a b. That's the intercept of the straight line. The rate law says if this is true, the rate equals little k constant times the b squared. Also, I wanted to review, did I write it down up here? I did. I wanted to review the naming descriptions of what versus what. Are you comfortable with that? Usually in science we put the dependent variable. No, wait, I got that wrong. The independent variable on the x, and we control when we measure time, but we have no control over what A is necessarily. So that's the dependent variable. So the concentration of A depends on the time, but in any case we say A on the y-axis versus time on the x-axis, or any general reactant versus time. So whatever's listed first in the versus dealio is on the y-axis. Whatever's listed second on the versus theme is on the x-axis. So this one would be the reciprocal of B versus time. Reciprocal of B versus time, 1 over B versus time, the reactant to the -1 versus time. If that indeed linearized it, the data, we would say it's second order in B. Rate equals little k times b squared. Also, the half-life here is not constant. The half-life keeps changing depending on how the concentration of B was in the beginning, or at any one point will determine the half-life from that point forward. Here's another common linear graph you'll see here and there. The natural logarithm of some reactant concentration versus time is linear. What would that tell you? Oh yeah, wouldn't that tell you that it's the reaction rate in R, reactant R, is first order? And there it is, some of the details. Natural logarithm versus the reactant. I'm sorry, natural logarithm of the reactant concentration versus time. So that's y-axis and x-axis, natural log of reactant versus time. That's linear if it's first order in R, and so therefore if that's linear, it's first order. The rate equals concentration to the first power. Here are the integrated rate law equations that we've practiced with, and you need to know how to use those, but don't memorize them, they're given to you. But another very important and handy deal is many reactions and even nuclear change, nuclear decay, proceeds in a first order fashion, and so the half-life is constant. Yay! So the half-life here doesn't change over time, it remains the same. So if the half-life is 1,000,000 years, in 1,000,000 years half of it, my reactant and nuclear stuff will be gone. 1,000,000 years is a long time. Unless it's a very slow chemistry, kinetics, it must be a nuclear change. Okay. What does it tell you? The answer is not a whole lot. Many times the concentrations of any reactants are here in green and B in orange. Concentrations versus time are not linear. So I know it's not zero order with respect to R and B, but maybe you've forgotten that a first order decay occurs more quickly than a second order decay, almost always. Yeah, many other things being equal, if we can keep them equal, the first order decays faster than the second order. Yeah, so I say again, the reactant concentration versus time, usually not linear unless it's zero order, and we saw that graph a little while ago. For second order, rate equals the constant with regards to B times the concentration to B squared. Or for first order, the rate, and I'm not saying these two R and B, reactant R and reactant B, I'm not saying that they are in the same reaction. I'm just saying that be aware that usually first order processes occur more quickly than second order processes. And first order, of course, means it's to the first power, and second order means to the second power. And we already looked at what those mathematical descriptions of these curves were. This one, did I write it down? Well, I will write one down. No, I won't. Yes, I will. I didn't. I thought I did, but I didn't. Okay, whatever. So this curve will be an exponential decay, and this is a reciprocal decay. Here's another really tricky one you might see. This is, I suppose, the rate on the y, concentration on the x. So if I look at how the rate changes depending on concentration, the answer is for zero order, it doesn't matter. So it's just a straight, non-changing, non-increasing, not decreasing rate as long as there is some K, or is some A reactant. With reactant capital R, if I graph the rate, here's the rate dr by dt versus the reactant concentration. For first order, that's just to the first power, and so it's R times some constant, and it rises linearly. And lastly, in the orange, the rate of change of B with respect to time is equal to some second order, capital B concentration squared, and some constant there. You better think about that one for a while. See if you can ask your TA a good question, or myself. And the last type of graph I have is this one. What does that tell you? Oh, I remember. This is called the natural logarithm of K, little k constant, rate constant, versus the reciprocal of the Kelvin temperature. If indeed, and usually it does, this comes out to be linear, then the activation energy for that reaction that generated this data, well, of course, as I make my reactants warmer, almost always the reaction rate goes faster, and that's reflected by the little k constant growing larger. And the activation energy is described by the slope of the line times the gas constant. Go ahead and make it a positive number because we really have to add in activation energy into the reaction for it to go. And the gas constant is given to you, but it's good to think about joules per mole Kelvin. And these equations are where this straight line comes from, because if I graph K2 and T2 at this point, say, and K1 and T1 at this point, and K3 and T3 at this point, and K4 and T4 at this point, I get almost always, many times, a very nearly perfect linear fit. And that's described sort of like by this two-point form. This two-point form kind of eliminates the constant A, which has other components which we may or may not be able to discern, figure out. So we do the two-point form, and therefore we don't have to worry about it. We just know that this point and this point are connected by the activation energy and the gas constant. Alright, that's enough for one day. Jeez. Thanks for watching, guys, and I'll see you in class too soon.